Hey everyone, welcome back, and you are listening to The Big Three, your favorite Canadian undergraduate podcast. I'm Dheepthi, and joining me is Bejal and Angad. We love talking about new discoveries from Hamilton's McMaster University and hope you are as amazed as we are with some of the groundbreaking work coming from our own school.
And with that, this week's hot topic is overcoming the limitations of vaccine distribution.
So, has anyone been watching the news lately? Big news from Pfizer, eh?
Yeah, I heard their COVID-19 vaccine was 95% effective. Really trying to one-up Moderna there.
I feel like this is great news, but what worries me about this is that people might start thinking that restrictions will be lifted soon.
That's true. I don't think many realize that producing an effective vaccine is simply just the first step. We still need to figure out a way to distribute these vaccines in large volumes without them becoming ineffective. And right now, there are major setbacks in the current cold chain method of distribution and storage.
Now, the cold chain isn't something that Ice Cube wears. Get it? Ice Cube. So the cold chain is actually a system in which the vaccines must always be stored in temperatures between 2 and 8 degrees Celsius from the point of production to dispensation.
So it seems like delivering vaccines to places where the climate is very hot can definitely pose a challenge, as it would be even harder to keep the vaccine's temperature stable. So maintenance of temperature is really important, yeah?
Yeah, well, vaccines are very sensitive biological molecules, right? And can lose their potency and effectiveness if they're exposed to temperatures outside a specific temperature range, like Bejal mentioned.
Honestly, I feel super lucky that here in Canada we have companies and funding to build proper cold chain infrastructure, such as large storage freezers, but I guess that's not the case everywhere.
And you're right. See, this was a huge obstacle during the Ebola outbreak, where vaccine distribution to different hotspots in Africa was very difficult, simply because they were unable to support the cold chain infrastructure.
Wow, it seems like the cold chain imposes a huge economic divide when it comes to vaccine distribution and availability.
You know, I'm glad you mentioned that because other researchers from the University of Chicago, Manchester, and Butler University have tried solving this using different techniques like modifying viral vectors, engineering a mutant antigen, and foam drying vaccines.
And although really promising, these methods were not cost effective and they required equipment that's not easily acquired either. But to go around this, a research team led by Dr. Leung, an assistant professor of chemical engineering here at Mac, came up with a low-cost, compact way to transport vaccines that works outside of the cold chain entirely.
You know, it's hard to believe that this work was actually inspired by the film coating on Listerine breath strips.
True.
See, these strips are coated with a sugar called pullulan, and that's what causes these strips to dissolve so quickly.
Wait, isn't that the sugar also used to coat produce in order to extend their shelf life?
Yep, that's the one. So this team knew that some sugars can stabilize biomolecules, such as proteins, at high temperatures, keeping them from losing their structure and function.
So the team decided to investigate this property with pullulan. They found that when a solution of pullulan was combined with another sugar, trehalose, it made a gel-like mixture preventing molecules from denaturing. Then they added an enzyme or bacteriophage, a type of virus essentially, to the mixture and dried overnight into the film. Now you've got a sugary film with these molecules suspended within it.
Basically, the sugars work as a team, where the pullulan makes the film while trehalose protects the vaccine from interacting with the environment and falling apart.
Exactly. And then these positive interactions help the biomolecule withstand high temperatures for extended periods of time.
So then they thought that why not see if the sugar film has the same effect in vaccines?
Exactly. So when they use this pullulan and trehalose film combination on two different types of vaccines, live attenuated and inactivated. The live attenuated vaccines use a weakened or modified version of a virus.
Yeah, and inactivated vaccines such as the flu shot contains the killed version of the virus.
Yeah.
Yep, and both types activate an immune response, training our bodies to recognize the live virus.
Yeah, compared to other vaccine types, these two are the most common, but also the most unstable, making their transportation difficult. So it would be important that this new technology works for both of them.
Right, and fortunately, according to Dr. Miller from the biochemistry department and researcher on this team, said in an interview with Globe and Mail that combining the vaccine types into sugars is as simple as stirring milk and sugar into coffee.
Seems too good to be true.
Well, see, once the sugars and vaccines were combined, the gel mixture was again dried into a thin film. So when stored at elevated temperatures up to 40 degrees Celsius, they found that the vaccines in the film maintained their composition and efficacy for up to 8 weeks.
That's great. That's amazing. But when it comes to administering the vaccine, how would you separate it from the sugar mixture?
Well, you actually don't need to isolate it again. This is an added bonus of using these films. See, upon injection, the vaccine or the film just needs to be dissolved into saline water.
Sweet. And since both the sugars have other uses, they are easy to access, relatively inexpensive, and already FDA approved. Also, it is a very compact way to transport pre-existing vaccines without refrigeration.
Yeah, it's a real game changer, and this would drastically reduce the costs of vaccine development since transportation accounts for about 80% of vaccine program costs.
I mean, this is an ideal approach, but the shift from the current cold chain infrastructure to implementing film-based transport would still require heavy investment.
Yeah, and to combat that, this team actually created a startup called Ilarix and are currently looking to partner with large vaccine manufacturers or industry leaders such as the Bill and Melinda Gates Foundation to secure capital and commercialize this system.
So, would this technology be compatible with current or potential COVID-19 vaccines?
Well, according to CDC, the vaccines produced by both Moderna and Pfizer are mRNA-based and don't use the live virus.
Although this vaccine type was not experimented with, in an email interview that we had with Dr. Miller, he stated that it's very likely that their solution would work well for live attenuated vaccines and other viral vector vaccines currently being developed for COVID-19, including Moderna and Pfizer.
It's amazing to see a team from our university contribute to creating a more accessible vaccine distribution program. It really goes to show the power of innovation and technology. With that, we would like to thank all our listeners for tuning in to the Big Three. Good luck with your exams and enjoy the long winter break.